Hi dear students, welcome to this online class on Aromatic Electrophilic Substitution reactions. You know that aromatic compounds like benzene are characterized by having delocalized pi electrons due to resonance. For example, if you consider benzene, it has got 3 pi bonds, and due to resonance these 3 pi bonds are delocalized. Due to that, aromatic compounds or arenes preferably undergo substitution reactions, not addition reactions. These pi electrons are stabilized due to this resonance, and the resist addition reaction instead undergo substitution reaction. So what is meant by substitution reaction? A reaction in which one atom or group is replaced by another. In benzene, one hydrogen atom is replaced by another atom or group. First of all, let us understand why arenes or aromatic compounds are susceptible to electrophilic substitution reaction. What is meant by electrophilic substitution reaction? A substitution reaction in which the attacking reagent is electrophile. We have learned about the orbital picture of benzene, wherein the pi bonds are formed by the lateral overlapping of p orbitals. Benzene has got pi electron cloud, one lobe above the plane and one lobe below the plane. So benzene is rich in pi electron, which is exposed above the plane of the ring, and below the plane there is pi electron. So it is pi electron rich, so that electrophile which is looking for electron will easily attack benzene. So that is why aromatic compounds like benzene easily undergo substitution reaction, that is electrophilic in nature. Now we will discuss what are the different types of electrophilic substitution reactions and what is the mechanism of each of them. First, let us go into the types of electrophilic substitution reactions. There are mainly 5 types. One is halogenation, number 2 nitration, number 3 is sulfonation, number 4 Friedel-Crafts alkylation, and number 5 Friedel-Crafts acylation. Famous 5. These reactions are taking place due to various reagents, and let us see what are the products formed here. During halogenation, H is replaced by halogen X, the general symbol. It can be fluorine, chlorine, bromine or iodine, mostly chlorine and bromine. In each of these reactions you can see one reagent which provides the electrophile and another reagent which acts as the catalyst. So here X2 in presence of FeX3. For example, Cl2 in presence of FeCl3. This FeX3 is the catalyst. So H is replaced by X, that is halogenation. So what is the product obtained? H is replaced by halogen, so you get halobenzene. The reaction can be seen like this. It can be visualized like this. This H is replaced by X. So the reagent X2 comes like this. We can show it like this. And this is what happens. H will combine with one X and form the byproduct as HX, and X will take the place of H. So the product is halobenzene plus a byproduct, that is HX. The second reaction, that is nitration. The reagent is collectively called nitrating mixture. that is concentrated HNO3, nitric acid, and concentrated sulfuric acid at a little high temperature. The reagent is HNO3. So here during nitration, H is replaced by NO2. This is the incoming group. So we can write nitric acid like this for convenience, like NO2OH. This is HNO3. So this H and OH will combine to form water. NO2 will take the place. So the product we obtain is called what? What is the product called? Nitrobenzene. Byproduct is HOH or H2O. The third reaction is sulfonation, where the incoming group is SO3H. H is replaced by SO3H. What is the reagent? Fuming sulfuric acid. What is fuming sulfuric acid? Sulfuric acid which is rich in SO3. You know, sulfuric acid is manufactured by dissolving SO3 in sulfuric acid itself, forming oleum, which is diluted sufficiently to get sulfuric acid aqueous solution by contact process. So sulfuric acid which contain excess of SO3 will be fuming. SO3 will come out as fumes. That's why it is called fuming sulfuric acid, which will contain excess of dissolved SO3. So this is the reagent. We can write sulfuric acid like this, SO3HOH for convenience. So the reaction is H will combine with OH, SO3H will take the place. The product obtained, I am writing it like this. The product obtained is H is replaced by SO3H. What is the name of the product? Benzene sulfonic acid. Product here is nitrobenzene in nitration. What is the byproduct during sulfonation? It's very clear. It is again H2O. Right? Now the last two, these are collectively called Friedel-Crafts reactions, which is of two types, alkylation and acylation. In both of the reaction, the catalyst is AlCl3, which is called Friedel-Crafts catalyst, which is most common. There are many other options of using Friedel-Crafts catalyst, like you can use Zn anhydrous zinc chloride, FeCl3, BF3, etc. can be used. This is most common, that is anhydrous aluminum chloride. During alkylation, the incoming group is nothing but R. H is replaced by R. In acylation, the incoming group is RCO, which is called acyl group. So what happens here? This is the reagent, that is Rx, which provide the electrophile. AlCl3 is the catalyst. So we can write alkyl halide as Rx like this. This is alkyl halide, which introduces alkyl group. So product of alkylation is a reaction in which alkyl group is substituted over benzene. So this is the reaction taking place. H combined with X forming HX as the byproduct. R takes the place. You get the product as, the product obtained is this one, R on benzene ring. What do you call this? Generally alkyl benzene. If R is CH3, it is methyl benzene or toluene. Byproduct is again HX. Coming to the last one, Friedel-Crafts acylation. As the name indicates, acyl group, that is RCO, is introduced into the ring. Reagent is RCOX. What is this? This is called acyl halide or acid halide, which is one of the derivative of carboxylic acid. We can write it conveniently like this, RCOX. Bonding is to be noted clearly here in acyl group, RCOX. So again, HX is the byproduct, CO connect on benzene ring. We can write the product like this, CO. C connection is C, carbonyl group is connected here, and like this, COR. C is attached to the ring. What is the name of this product? Generally called acyl benzene, plus byproduct is again HX. Right? These are the 5 most common electrophilic aromatic substitution reactions of benzene. If you consider various other reactions of benzene, various name reactions, and if you look into the mechanism, you can see that most of the reactions are of this type, that is electrophilic substitution reactions. So that's about the types of reactions. Now we have the mechanism of this electrophilic aromatic substitution reactions. In the mechanism, we are very much concerned about mechanism in this module according to the syllabus. For each of these 5 reactions, we should learn the mechanism, right? First, we will propose a general mechanism and then go to different types of mechanism. First of all, the general mechanism. General mechanism. Okay, before that, see what all we discussed here. The electrophilic substitution reaction can be generally represented like this. For example, like this, benzene. We are showing one H explicitly because it is going to be substituted. React with one electrophile which is generally E plus. Electrophile is shown as E plus. Not necessarily. Electrophile can be even neutral. We will see such examples later. This electrophile attack benzene and it replaces H and form the product, that is electrophile is substituted on benzene ring and H will come out as H plus. See, in any equation, any chemical reaction, atomic balance as well as electrical balance is an important guide. See, this side you have a total 1 positive charge and therefore H should be H plus to maintain the charge. So this is a general representation of electrophilic aromatic substitution reaction where this electrophile changes in all the 5 reactions. Now coming to the mechanism, we take the general mechanism first. General mechanism. See, the mechanism involves 2 steps, right? There are 2 steps in this reaction mechanism. Before we consider the 2 steps, first of all we'll write what is called generation of electrophile. See, in this mechanism, the first step is attack by the electrophile on benzene ring. But before that, we should show what is the electrophile. So, generation of electrophile is to be shown first to explain the reaction. So, let us show generation of electrophile in general. Let us write the reagent is Ez, right? If the reagent is Ez, we can show that this reagent can undergo heterolytic fission. Say for example in the favor of Z, this bond is cleaved in this fashion. So what you get, E plus is 1 because this bond pair is given to Z, so E become E plus Z minus with a lone pair. This is the electrophile. So this is how electrophile is formed during the reaction, and this electrophile will attack benzene ring. Z minus can be called nucleophile because it's opposite. Better we call this as Lewis base because in the mechanism we will see that in the second step H is removed as H plus or proton for which a base is required. So this base will be used up in the second step. Now coming to the 2 explicit steps. Step 1. Remember this reaction involved 2 steps. Step 1 is attack of the electrophile. We can differently name this step. Due to the attack, benzene form a sigma complex or an aluminium ion. We can name the step as formation of aluminium ion. We will understand what is aluminium ion or sigma complex. formation of sigma complex or formation of rhenium ion. Let us show this reaction, this step. See, benzene is shown with the bonds. 1H is explicitly shown, which is going to be replaced, and plus this electrophile form is coming here. Now it is attacking. See, according to curved arrow formalism, you should show the arrow like this because this is a source of electron, not the other way around. Okay, this is a slow step comparatively compared to the second step. So what happens? You get an intermediate. What is the structure? These two bonds are intact. This bond is broken or it is taken out to form bond with electrophile. So electrophile form a bond using this pi bond. So what happens to this carbon? It get the positive charge because this electron is lost by this carbon, so it get the positive charge. Electrical balance is there. This positive charge on electrophile is appearing here now. This is a carbocation. Since this is an aromatic compound, we call rhenium ion, just like we call carbonium ion. This is rhenium ion. This is also called sigma complex because the bond here formed by electrophile with this carbon is a sigma type. So it's called sigma complex. It's a complex, right? Now, the importance of this intermediate is that it is resonance stabilized because there is conjugation. This pi bond can move to this place and you get the next structure like this. Positive charge appear here. Then this pi bond move to this place. We get one more structure. That is like this. Now positive charge is here. So you have three structures, we put it in bracket. So this sigma complex is resonance stabilized. That is very important. Resonance stabilized sigma complex or rhenium ion, right? In organic chemistry, there is a general rule that stabler the intermediate, faster the reaction. Stabler the product, faster the reaction. If it is somewhat stabilized, there is all possibility for its formation. So this reaction do occur. This is the first step. Now, among scientists, there is a different view that before this electrophile attack and form the sigma complex, there is a chance for forming a pi complex as well. And the initial stage of the reaction, that means, see, when electrophile is approaching this benzene for attack, it is a pi cloud which is projected out. So there is a chance for forming a bond between electrophile and this pi orbital, the empty orbit of electrophile and the filled pi orbital of the benzene ring, forming a pi complex. It is initially formed, but eventually at a later stage it transforms into a sigma complex, right? Finally, it is a sigma complex which exists. Now the second step. Now this can be written, it is equivalent to a resonance stabilized structure, or resonance hybrid can be shown something like this. We can show like this. A positive charge is delocalized over 5 carbons. We can show like this. See, this delocalization is not complete. This carbon is sp3 carbon, all others are sp2. So it is a partially, this delocalization is partial, not complete. So compared to benzene, benzene is fully resonance stabilized, but this is partially resonance stabilized. Anyway, it is stabilized by resonance. Now we go to the second step, step 2. So electrophile has come in. Now what should happen? Hydrogen should go out. So that is loss of proton. So the second step is loss of proton or loss of H plus. loss of H as H plus. That can be shown like this. See, this is the resonance stabilized rhenium ion sigma complex, which has this E and H over here. Now let me show, now let us consider this base which is present here, which is formed in this generation of electrophile. This Z minus of the base is shown here, which is having lone pair. This base will take away this H as H plus. It will abstract H plus. Naturally, consequently, this bond will get back to the ring. In the first step, this pi bond is taken out. In the second step, if this bond comes back to the ring, you get the product now as, it is a fast step comparatively. You get the product now as, when this is bond is given back, it will go back to the original electronic structure, and it is now E over here. This H plus will combine with Z minus and form HZ, that is a byproduct. So we got the product. So these are the two steps involved in electrophilic aromatic substitution reactions of benzene. Okay, we have to consider now various examples, the mechanism of the 5 different reactions one by one in the next class. Thank you.